Okay, so thank you all for coming. We're extremely happy to have Shu-Heng Shao visiting us today from Stony Brook, and he's going to tell us about non-invertible symmetries in nature.
All right, thank you everyone. It's good to be in this really lively group. So I'll talk about this series of work I've been doing with my students, Yicho Choi, and my longtime collaborator, Ho Tao Lan, and with a bunch of other my collaborators. The talk will be mostly based on this paper that appeared in May. It will also be based on the upcoming paper, finalizing the draft. This one will be about axiom. The first one will be about QED and QCD. Also check out this very nice paper by Clay and Contarov, which appears around the same time as this paper. And this talk will be based on some recent development on generalized global symmetry. So some of these papers of mine that appear in the past year will also be relevant, and I will mention it. So the title of the talk has non-invertible symmetry, but that's not where the talk will start at. We'll start with a very familiar story. Just massless QED, 3 plus 1D. And I will assume the gauge group to be a compact U1. If the gauge group were R, then I have nothing smart to say. This is an assumption from the very beginning. I assume the charge of the Dirac fermion is 1. It's massless. And I'm sure everyone of you has seen this equation before. In fact, I believe the equation of motion is on one of the walls around the stairs. Now, classically, this Lagrangian has axial U1 symmetry that rotates the Dirac fermion by a gamma phi matrix. Now, alpha is a 2 pi periodic angle. Don't worry too much about the factor of 2. It's there so that when alpha is 2 pi, this is a trivial transformation. Because when alpha is 2 pi, this is a minus 1 as part of the gauge group. Adler-Bell-Jackiw famously showed that this classical symmetry, the axial symmetry, suffer from an anomaly, in the sense that even though classically it is a symmetry, quantum mechanically it isn't. The ABJ anomaly was discovered in the late 60s to explain the neutral pion decay problem. And it successfully determined the coupling, pi 0 FF, in the chiral Lagrangian. I used the differential Born notation, so F wedge F will be F mu nu, F tilde mu nu. You break it into the components, but I prefer the differential Born notation better. All right, so that was all well known back in the 60s. But conceptually, there's something just very, very slightly counterintuitive. Usually we celebrate when we discover a symmetry. If you think about it, in ABJ is the opposite. ABJ told you that naively there is a symmetry, the axial symmetry of the classical Lagrangian, but that actually there isn't. So how come we can learn all these fascinating quantitative results from the absence of the symmetry rather than the presence? And of course, in the actual QED and QCD story, the fine structure constant is very small in the real world. So we can effectively treat the electromagnetic gauge field as a background gauge field. And then all the arguments made there can be understood as a two-loop anomaly matching condition. And nothing is wrong with that. Everything that has been said in the textbook is perfectly correct. But wouldn't it be nice if we can reinterpret this classic result from the existence of some kind of generalized global symmetry rather than the absence there? And that's the main motivation of it. Another motivation is that when you ask someone, is the U1 axial symmetry a symmetry in the massless QED, you get a whole spectrum of answers. Let me just list a few. When I grew up, I always thought the answer is just number 1. It's not a symmetry, period. That's the whole point of it. The axial symmetry is not really quantum mechanically a symmetry, and therefore neutral pion is not really a Gauss boson, even in the massless part. And that's why it emits a non-derivative couplings to the photons. And that's why in the lab, you can actually see such a dominant decay channel into the two photons. But as we grew up, we find out that even though it's not quite a symmetry, it still implies something non-trivial. For example, the helicity in any scattering amplitude of massless QED has to be conserved. By helicity, I only mean the helicities of the electrons and the positrons, not of the photons. And sometimes people will say that, yes, actually the axial symmetry is a symmetry, but in flat space-time only. And that's because the anomaly, the symmetry is violated by non-trivial instanton, and there's no non-trivial instanton configuration in flat space-time for a B linkage. That's also a perfectly valid answer. There are also some more, maybe I would say more vague answers like, yeah, it is a symmetry, but it's not aging variance. Yes, it is a symmetry, but it's an anomalous symmetry. I don't know what that means. Sometimes people also say it's a background symmetry. The list goes on. But I would hope that, if someone wake me up in the middle of the night and put a gun at my head and ask me, is U1A a symmetry or not? I would like to give a straight answer. I would just like to just say yes or no. I don't want to give this whole list of answers. And that's the motivation of the talk. I want to get a straight answer. Now, the upshot of the talk is that we will show that the continuous invertible U1 axial symmetry in the classical Lagrangian is not completely broken by the ABJ anomaly. Rather, the ABJ anomaly turns it into a discrete and non-invertible global solution. Each one of them labeled by a rational number. We'll see how that comes about. In that sense, in the pion Lagrangian, this coupling between the neutral pion and the photons can be re-derived by matching the non-invertible global symmetry in the UDQCD. So we have now turned the ordinary ABJ anomaly argument into a matching condition of the global symmetry. So in the most offensive, to put it in a maximally offensive manner, one can say that the neutral pion decays because of this non-invertible global symmetry.
May I ask?
Yes.
To test how powerful it is, that you said in the standard argument relies on alpha being small, so in some sense it's denoted in alpha. So isn't this more powerful argument? Do we have something which goes beyond?
Yeah, that's a tricky question, right? Because as you turn alpha to be very large, QED is eventually not UV complete.
But you might take it small, but ask questions about like alpha squared corrections.
Yeah, you're asking, is there anything more quantitative?
Right. Yes.
Yeah. So the matching will be quite quantitative. We'll see. I think it's let me make sure. Yeah, the matching will be exact. The coupling here will be exactly determined, just like in the ordinary example.
But that's the ordinary. That's on as far as physical thing, like decay width. It really says it's a leading ordering.
But the leading decay rate is already determined by this coefficient.
Right.
So like we know the one, the anomaly coefficient is one loop exacta when we do this calculation, right?
Well,
that's also true.
But
like we know that is exact. Like you don't have to do higher order in alpha.
Well, but the decay width is not one loop exact, right? So
I'm only going to reproduce this term.
Right.
Yeah, indeed, there are other channels that are contributing to
this is
other
the most
processes.
robust prediction from this. There are finer.
I think the story I'm going to tell today, I mean, it's just a reinterpretation of everything we know. And everything that has been said previously is perfectly correct. So it would be nice to put everything into a new, I would say a more coherent method. And I do believe there are further applications of these symmetries down the road. In fact, there were some new papers in some other contexts using those symmetries. And I'll be happy to talk about those new predictions. But as far as the pion goes, we know the neutral pion decays into photons. And I'm not going to say, I'm not going to produce anything. Maybe there's something more one can compute. Okay, so this is where we were. So that's the punchline, and now we can go to the bulk part of the talk. So before we talk about generalized symmetry, let's set a stage for ordinary symmetry and how one thinks about global symmetries in a general context. So for concreteness, let's consider quantum field theory, relativistic quantum field theory, with a conserved network current, J mu. And it's associated with the U1 global symmetry. The conserved U1 symmetry operator is to take the zeroth component of the current, integrate it over the whole space, and you exponentiate it. That gives you a unitary operator, performing a rotation by angle theta. Now, in relativistic quantum field theory in Euclidean signature, the time direction, this zero direction, is on the same footing as any other direction. So it's very natural to generalize this expression in Euclidean four-dimensional space-time to this one. So you view the J as a one form, take the Hodge star to make it a three form, and you pick any closed three manifold M to integrate that three form on that manifold M. And you get an object, U theta of M. When M is your whole space at a given time, that gives you an operator acting on the Hilbert space. It's a unitary operator implement the symmetry transformation. When M extends in the time direction, but localized in some direction in space, that gives you a defect that twists your quantization, that implements a transformation as you bring your field around space. Throughout the talk, I will focus on relativistic quantum field theory in Euclidean signature, where the distinction between operators and defects is not that important. For most of the cases, they are related by a big rotation. But sometimes the distinction is crucial, and I will comment on that when necessary. Oh, sorry, yeah, there was a question.
Just the star operator.
Yes.
I'm not too familiar with this notation. Can you just elaborate? You said it turns into a three form?
Yes. Well, to make it a three form, it's called a Hodge mu. We have J mu. Then we raise the index. We have the Chilita symbol, which has four legs. We contract that, and there might be some factor of
So it's
one.
just a contraction. Yeah, sure. Thanks.
In the case when it's an operator, U theta, the whole point of the conservation equation is that this gives you an operator that's conserved, meaning that when you take the time derivative, it vanishes. That's easy to see. You take the time derivative, you hit the time derivative on this object, and you commute it into the integrand, and apply the conservation equation, get the total derivative, and that tells you why the operator is conserved. And that's why it qualifies as a symmetry. But as I said, in Euclidean signature, there's nothing special about the time direction. So the conservation equation should be upgraded to the fact that this object, U theta of M, depends on the choice of the closed three manifold topological. So it means that it's not only conserved under time evolution, you can also turn it this way, that way, you can deform it a little bit, as long as it doesn't pass any charged object, any correlation function should be invariant. And that follows straightforwardly from this expression by applying the divergence theorem, as we learned in undergraduate electromechanics. So this is the connection between a global symmetry and topology. A global symmetry is naturally associated with such a topological operator slash. So that's for the ordinary symmetry. Coming to the QED story, we can define this axial current, which is a fermion bilinear with an important factor of gamma phi. It's not conserved in the sense that the conservation equation has a non-trivial right-hand side. It doesn't vanish on the right-hand side. Here, F is the gauge invariant field strength 2 form. Naively, you can still define this operator by integrating star JA on any three manifold. But as I said, it's not going to be conserved. In 1969, if you look at Adler's original paper, he defined the following. You take this combination, star JA minus 88, turn sinus. The thing in the parentheses is not gauge invariant. As you do a gauge transformation of your capital A, this term transforms. You might hope to integrate it over a 3-manifold to make it gauge invariant. But that's generally not the case. If M is R3, then it's gauge invariant, and that's what Adler did in 1969. But more generally, you expect if there's a global symmetry, you should be able to define the topological object on any closed 3-manifold. And the fact that the coefficient here, multiplied by r over 2, is not properly quantized means that this expression, the whole thing, is not invariant under large gauge transformation. So the status at this point is that you can either have a gauge invariant operator, which is not conserved, or you have a gauge non-invariant operator, which is formally conserved. But since it's gauge non-invariant, I don't know what I'm talking about. That was the status after 60. And it just seems that there's no conserved and gauge invariant operator in massless QED.
Sorry, because you're not talking about soft anomaly here. Your F, it's really dynamic. So there is
Absolutely.
there's alpha then on the right hand side, right? So
Well, so I probably, there's no alpha on the right. That depends on how you normalize the F. So here I normalize the gauge field such that the field strength when integrated on any surface is 2 pi times A. Yeah. So this is a difference in the normalization. So in particle physics, or when you do scattering amplitudes, it's conventional to normalize your gauge field such that the Maxwell term is just F mu nu times 1 over 2.
but if I think just in terms of physical EMP, there is alpha.
Well, it again depends on your normalization.
Like 1 over
of the
4
gauge
E
field.
squared.
Yeah.
Can I turn it into this?
I just put in the G's in the definition of F.
That's right.
So there's alpha.
Yeah, I would say both are physical. One of them is more convenient to compute scattering amplitudes. The other is more convenient to keep track of the global part. You talk to a mathematician, he would probably prefer this normalization because then the field strength is a connection with properly quantized term numbers.
But my confusion is stems from the fact because you really want to think about not soft anomaly, but
It's not a
dynamical anomaly.
Absolutely.
And so if I put alpha there, and you're talking also about massless QED.
Yes.
So at what scale I put this out? Because if I go to deep IR,
It's 0.
it's 0. It's completely screened. So at what scale I'm supposed to take that alpha there? If I
What do you mean? I still don't get it. In any case, it's just a redefinition of F. Again, I can also write it here.
But what he means is that, okay, like in massless QED,
Yeah.
in the infrared, the gauge coupling goes to 0.
Right.
So like you might be worried you're multiplying by 0 various places.
Well, in the IR, we know what it is, right? It's just a free theory.
yeah, so
Right.
this normalization I'm doing. So at what scale you are doing this normalization?
At any scale, I can do that renormalization. It's only the limiting point. Well, even in the deep IR, it's a free Maxwell, and I'm using that normalization.
So I guess at what scale do you imagine you're evaluating the coupling?
At any scale, at any weak coupling scale, doesn't matter.
Except in the far infrared.
In the far infrared, we know what it is. It's a free Maxwell and
Okay.
a free Dirac break. Anyway, that's my normalization.
I think this question is the difference between terms, I mean, formulae like this, or terms in a perfect Lagrangian, and full physical quantities observables. You're worried about the value, for instance, of the actual decay width,
Right.
for instance, which does involve the electromagnetic coupling. Right, and certainly you would need to know what scale that's evaluated at. I mean, you agree, if you hadn't been discussing this term, but you'd instead been telling us about the width of the pi zero, right, you would need to know the the scale there, and I think that's resolved by the fact it's exactly at the scale of mass to the pi zero, right? That's the thing that determines it, right? Self-consistently. So I think you have to add in the extra element of what process you're really looking at. You don't get it from just looking at this term. So
Yeah, I'm not sure I follow the discussion. Anyway, if you don't like it, you can put the e squared back. It's just a rescale.
Well, but if you put the e squared back, then I would ask you at what scale you evaluate that e squared.
Any scale that's weakly coupled.
no, that's incorrect.
I don't understand. Why is that incorrect?
No. It's incorrect because you have to do it at the scale of pi zero. You have to ask a physical question. You have to have a result to a physical
The
question.
physical question I'm asking is whether the current is conserved or not. It's violated by this.
No, but if you were to
But
phrase the thing,
no one is sandwiching anything in between, like some in and out. Like at this level is fine, right?
Well, I hope I'm not
We're
saying
not
anything
evaluating some,
controversial, right? Adler-Bell-Jackiw wrote this equation, and I only did the rescaling for my own convenience.
no, I think the issue is after all, you're doing a reinterpretation of classic results. None of us are
No,
disagreeing.
I'm not doing any reinterpretation. This is a literal equation that you can find
Right now,
in
there's
the
not-
textbook.
There's no
I'm not doing any
interpretation.
reinterpretation. Many people thought this is a
Sorry,
reinterpretation, but if you look at 1969 paper by Adler, it's there.
I realize that. I read the
Yeah,
paper
yeah.
very well. So my thing, I think you're misunderstanding what the issue is, right? Which is you're going to go on to
Yeah.
do things. So we should be careful about how we're defining things.
So I think probably when we get to the point of computing, the decay rate of the pion, we should revisit this question. Maybe now, like we can continue.
Yeah, I mean, I'm saying, and everything I said was known in 69.
One question about this gauge invariant version.
Yeah.
You said it's not gauge invariant and the large gauge transformations only.
Yeah.
Correct. Okay.
And R3 is fine.
And R3 is perfectly fine.
Current derivative, right? What is the boundary term?
Or even a decimal gauge transformation is just convolution.
So you just need to be something with the gauge parameter like stays non-zero at the boundary of this manifold.
That's right. Yeah. So at this point, there's no conserved n-gauge invariant operator. And as I emphasized again and again, I'm not saying anything new yet. This is all well-known stuff. Now, we go to the next slide. Still nothing is new. I'm being less ambitious and take my rotation angle alpha to be 2 pi over a positive integer. This integer can be anything, just some positive. Then I put that back in this operator that is not gauge invariant, and I look at it again. It's still not gauge invariant because of this red term. This red term has a coefficient being I over 4 pi n. And I should say that this is the reason I want to normalize my gauge field in the way on the blackboard. It's because with that normalization, it is known in the literature that this term, this red term, is only going to be invariant under large gauge transformation if the coefficient is an integer over 4 pi. But here it's different, it's fractional. So we still haven't made much progress because of the fractional consignment. But let's zoom in on this term and forget about where it comes from. And view this term as a 2 plus 1 dimensional action on some manifold n. This term appears in another famous context, the fractional quantum Hall state. This is used as an effective action for the filling fraction 1 over n fractional quantum Hall state in condensed matter physics. I put it in quotation marks because it's not gauge invariant. In the context of fractional quantum Hall state, fortunately, there's a well-known fix to this gauge non-invariant action. And the fix is to replace it by this blue Lagrangian, where we have introduced an additional gauge field little a. The blue Lagrangian is gauge invariant. More precisely, the path integral of the blue Lagrangian is gauge invariant. One way to see that is that every term is an integer over 4 pi. Heuristically, the relation between the two Lagrangians is that you can integrate out little a and get this relation. You substitute this back in, recover the red Lagrangian. But this is not a legal manipulation because both little a and capital A are properly normalized. They are properly normalized in the sense that their field strength should, when integrated on any closed to surface, should be properly quantized. And you cannot divide the properly quantized gauge field by a factor of n. And that's to be expected, because the red Lagrangian is gauge non-invariant, whereas the blue Lagrangian is gauge invariant. There's no way for you to do a legal manipulation to relate the gauge invariant Lagrangian to a gauge non-invariant. In any case, in the context of fractional quantum whole state, this is a precise and gauge invariant Lagrangian.
So I'm just confused. I
Yes.
mean, in the very last thing you've written in the slide,
Yeah.
presumably you get there by like this. That's just the equation of motion for little a.
Yes.
So how can that be illegal? I don't understand what you mean. Like there's something wrong with this.
The equation of motion more precisely is n times little a being capital A. But the important thing is that you cannot divide it by n,
I
because
see.
they are eventually zero. They are properly wrong. It's that division. The mistake lies in the division. Okay. So motivated by this discussion in the fractional quantum Hall, let's go back to QED. This is where the new stuff came in. Up to this point, everything was known back either in 69 or 82, maybe not 82. But now, the new thing is that we would like to take this operator from QED, this U-hat operator, which is not gauge invariant, and replace the problematic piece, the red Lagrangian, by the blue. And I use a different symbol to denote it, because they're really different objects. This is not gauge invariant. This, however, is gauge invariant. This is an operator in QED that involves an auxiliary field little a that only lives on the three manifold where I define this operator. It's gauge invariant because all the coefficients here are properly quantized. It is also conserved, and more generally topological. That fact is less obvious. And I'm not going to prove it during the talk, but you can find the proof in the paper. Heuristically, you can say that the blue and the red are basically the same locally, and we understand why the U-hat operator is conserved. It follows from the anomalous conservation. But if I use that heuristic argument, I'm just going in a circle. And there's a more rigorous argument presented in the paper. So it seems that we have constructed a new operator that is both gauge invariant and conserved. At the level of the slogan, we can say that we use a fractional quantum whole state to cure the ABJ anomaly. But there's no free lunch. The price we pay, which I should say is really a feature, not a bug, is that this new operator D, even though it's conserved and topological, is not a unitary operator. In fact, it's not even invertible. I'm not going to show why it's not invertible. It basically follows from the fact that it contains a fractional quantum whole state. The fractional quantum whole state is a non-invertible phase in condensed matter physics. I'm going to demonstrate why it's not unitary. So this is rather bizarre, because usually if you have a conserved operator that implements a symmetry, and symmetry is usually implemented by a unitary operator. But this one is not. And we can see that very directly. We just multiply D with D dagger. The key is that when you define this operator D, you have to use an auxiliary field little a. And there's an auxiliary field little a for each operator D and D dagger. So I have an auxiliary field little a and an auxiliary field little a bar. And you can see that the naive axial rotation part is cancelled. But you are left with a somewhat complicated expression that involves two auxiliary gauge field little a and little a bar, and the bulk magnetic field E capital A. This is almost like a magnetic flux operator because it depends on D capital A. However, it's supported on the three manifold, and that's rather bizarre. Usually, we think we can only define a magnetic flux operator on the two surface, but this is a magnetic operator on the three manifold. This object, whatever it is, the most important thing to notice is that it's not one, and therefore D is not a unitary object.
So this is, sorry, I'm not an expert. This is still topological. This is like a transgression form of something.
A what?
This is like a transgression boundary form. Transgression from, like boundary term for the Chern-Simons.
Oh, this is a Chern-Simons term.
You know, I'm talking about the last.
So last one is also a
Mixed
Chern-Simons term.
transgression, yeah. Mixed Chern-Simons.
It's a mixed Chern-Simons term. This is in 3 dimension, not in 2D. If you cut it open, then there might be some boundary.
So is it some new topological operator? Because it's again,
This object?
yes.
Yeah, so this object is called the condensation defect. So it was studied in the condensed matter theory, field theory context long ago, and it has recently been studied in the high energy physics context. But you are right, it's a new operator.
But I think this is what mathematicians call transgression from. It's not new. What sense?
It uses Chern-Simons form, but it's physically a new operator.
By new, I meant in addition to D and D.
That's right. In fact, this one is, in a sense, even more elementary than D. This one, the condensation defect, follows just from the fact that there's a magnetic one-point symmetry. Whenever you have a higher point symmetry, there's a procedure called higher gauging, which I'm not going to talk about in this talk, that can give you the condensation. The rather surprising thing is that you can actually take the square root of this defect and get it. But in any case, I could have given another whole talk just about the condensation defect, but the main player of this talk will be about D. And the only thing we need to know about D times D dagger is that it's not 1. And all the mathematical ingredients are just Chern-Simons.
Sorry, question.
Yeah.
But on the Hamiltonian level, it will still commute with the reduced density matrix or something. So it's in this sense, it's a symmetry.
So both D and C, I would call them symmetries in the sense that they commute with the Hamiltonian as operators. And more generally, if you insert them in any Euclidean correlation functions, the dependence on the support of these operators or effects are topological.
Thank you.
Yes, we comment, like, can you comment on like the very last sentence on this slide?
Yes.
What do you mean from higher gauging on the C and subgroup of the UM magnetic?
Yeah. Okay. Yeah, I can. So sometimes I give a whole talk about that.
Right.
So, but I can just briefly say that. So higher form symmetries are topological operators of higher coordinations, and you can also gauge higher form global symmetry. Gauging typically brings you from a quantum system number 1 to quantum system number 2. It changes the quantum system. Now, in this paper that I wrote in April, we define a notion of higher gauging. Higher gauging.
I guess my question is more about like the CN group of the U1 magnetic one for symmetry.
Yes. So in QED,
Yeah.
You have a magnetic U1 one-point symmetry. You can consider it as a
Okay. Okay.
the generator of that operator would be, e to the 2 pi I over n, e to the I over n times the magnetic plus actually it's over there. And there's this machinery called higher gauging that you can use a discrete higher form symmetry to generate topological. Anyways, I'm not going to spend too much time about the right-hand side. The upshot is that it's not 1. So I'm going to summarize what we have discussed so far. We start with an operator that's gauge invariant but not conserved. And then we talk about this operator, half of the hat is somehow missing. It's not gauge invariant but formally conserved. And lastly, motivated by fractional quantum Hall, we find an operator that's both gauge invariant and conserved, however, it's not inverted. Still, it qualifies as a symmetry because it commutes with the Hamiltonian, and in Euclidean signature is a topological operator /. That was the case when alpha is 2 pi over n, the rotation angle. It's easy to generalize it to arbitrary rational angle with 2 pi p over n with p and n cosine. All you have to do is to replace the 1 over n fractional quantum Hall state by p over n fractional quantum Hall state. This is something that our condensed matter physicist friends do for a living. And there is this 2 plus 1d TQFT that fits the field. I'm not going to say any details about this TQFT. You can see this reference for example. So to conclude, the continuous invertible U1 axial symmetry is actually not completely broken by the ABJ. They are resurrected as this D operator. It's both gauge invariant and conserved. However, it doesn't obey group-like multiplication law.
What happens if U1 were non-compact? And at this stage it would be different?
The gauge group? Right, yeah. If the gauge group were non-compact, then we didn't have the large gauge transformation in the first place, and you could have just used the U hat operator to get all this symmetry. So the objection wasn't there for a non-compact gauge group in the very beginning. This operator. If the gauge group were non-compact, this operator is actually gauge invariant because there's no large gauge transformation for a non-compact gauge group, and you can just stop there. And that's essentially what Adler did in 1965 by working with non-compact space.
And it's very important that this non-invertible symmetry is global.
It's a global symmetry.
Yeah.
Yes, it's an actual topological operator exists in the theory. So it's a global symmetry rather than a gauge symmetry. In fact, later on we will see that it acts non-trivially on gauge invariant operators.
But like, I mean, there is also like no way you could define a version of this where, you know, this is somehow like a discrete non-invertible gauge symmetry in some way.
Well, you're asking, can I gauge it?
Yeah.
That's an interesting question. So we
like from the point of view of where you start, like if I think of it starting from a U1 axial symmetry
right.
that has an anomaly, then like I know I kind of get it. So I cannot like go in that direction, but maybe there is some.
No, but I think anomaly can mean different things, right? In the context of QED, ABJ anomaly means that a classical symmetry fails to be a non-mechanical symmetry. In other contexts, you can have the honest-to-God global symmetry, but there's an obstruction to gauging it.
Yeah.
And here we are in the former case. So far we have resurrected ABJ anomalous global symmetry back to life. But you are totally correct that then, now that we have the symmetries, you can ask, can you gauge it? I suspect the answer is no, because already in the free Dirac fermion, the axial symmetry has a self-anomaly. And that's outside the scope of this. All right. Okay. But you can ask, why should we think about these topological operators or defects as some kind of symmetries? Well, for that we have to go back a little bit in time to see, to summarize some of the development in recent years. So it has been realized in the past maybe 5 or 6 years that various topological operators in quantum field theory should be viewed as a generalized global symmetries. They are not implemented by unitary operators, but they are in many ways are just as good or even more powerful than ordinary global symmetries. We should welcome them to this big family of symmetries. It is discovering a variety of quantum systems. So before 2021, before November last year, most of the examples were in 1+1, for example, in the Ising model. In almost all the rational conformal field theory, there's a non-invertible symmetry, and he finds an expert on that. And starting from November last year, starting from these 2 papers and many others, there was a new class of construction of non-invertible symmetries in higher space-time dimensions, including our dimensions. And in many quantum systems, such as the axion system, Maxwell theory, Young-Mill theory, it has been realized that there's a rich variety of non-invertible symmetries. I should say that this is not just some high-energy theories fantasy. They can also be realized very concretely on the lattice. And recently, mathematicians have also formulated that in a rigorous categorical. Let me give you some argument why we should include them as a generalized global symmetries. First of all, they are useful. This is not just some rephrasing of known phenomena. Especially 1+1D and also in higher space-time dimensions, they lead to non-trivial selection rules and conservation laws that were otherwise unknown. Second, which is related to Isabel's question, is that just like ordinary global symmetries, these non-invertible symmetries can sometimes be gauged in a general manner. Now, if there's an obstruction to gauging them, then they have a generalized anomaly. And that leads to a generalized two-group anomaly matching condition, which gives you non-trivial constraints on renormalization group flows. There are many examples in 1+1D. And for example, you can see this one for applications in 1+1D addresses. Then finally, in quantum gravity, there are many conjectures about global symmetries, H symmetries. In particular, it has been argued and proved to a certain extent that there shouldn't be any global symmetry in a full-fledged quantum gravity field. Recently, this no global symmetry conjecture is also argued to generalize to the absence of invertible and non-invertible global symmetries. And by including the non-invertible symmetries in the conjecture, it consolidates different quantum gravity conjectures. For example, it brings together the no generalized global symmetry conjecture with the completeness hypothesis. So from November last year, there has been a lot of development on construct. Yeah.
About that point, so are they? Is it established now that these two conjectures are equivalent?
Under some assumptions. 2+1D is easier to show. 3+1D is a little bit subtle.
So even if you include non-invertible symmetries, it's still not settled whether these two conjectures, completeness and no global
In
symmetry.
3+1D, it's a little bit subtle. So in the past year, there has been a lot of developments on this new kind of global symmetries in 3+1D lattice and continuation. And some of these constructions applies to quantum field theory that are invariant under gauging a discrete higher form global symmetry. So this is like a generalization of the Cramer's one-year duality. And in that case, you can generally you can start with the quantum field theory and gauge a global symmetry on one side. And that creates some topological interface separating two different quantum field theories. In the case when they are isomorphic, it gives you a topological defect. And that gives you a rigorous proof why the operators we discussed earlier are topological. Now, coming back to QED, we can say a little bit more about this topological operator D. So what does it do? First of all, it acts invertibly on the fermion operator, just like an axial rotation. And therefore, it leads to all the familiar selection rules that we are familiar with in massless QED. For example, in massless QED, you can say that using these non-invertible global symmetries, we know the helicity of the electron and the positron have to be conserved. You can look at Paskin and Schroeder and see how they explain the helicity conservation. They use the gamma 5 matrix and move it around to show that if the helicity is violated, then the amplitude has to vanish. Of course, that's a perfectly correct argument, but you can see that they didn't want to mention the axial symmetry in chapter 5 of Paskin and Schroeder, because they knew down the road the symmetry is going to be anomalous, and making the argument using symmetry will be dangerous. And now you can use this more fancy highbrow argument to say that there's actually an exact global symmetry explaining the helicity conservation.
But for that conservation, it doesn't matter whether it's compact or non-compact. So
absolutely, absolutely. You can also say that the gauge group is R, or we only care about flat spacetime. Absolutely. So I'm not advocating that Paskin Schroeder should be rewritten, but I'm just saying that this is an alternative perspective of the phenomenon. It gets more interesting when you think about how this operator acts on the two hoop lines, namely the word line of the monocle. So let's picture a Euclidean configuration where you have this three-dimensional topological defect set up somewhere in space-time, and you bring a two hoop line past this defect. What happens is that as the two hoop line go across the defect, it experiences a Witten effect. The theta angle is shifted as it goes through the defect. And Witten told us as the theta angle is shifted, the two hoop line becomes a dionic line with fractional electric charge. But what does the fractional electric charge mean? It means that it's not a genuine line anymore. It's attached to a branch cut. This is very similar to the branch cut of a disorder operator in the Ising model. That the Kadanoff studied, for example, in the 70s. So the two hoop line started its life as a genuine line operator, but it turns into a surface operator ending on the boundary. And that's a hallmark of the non-invertible action.
In the sense that if I were to bring back the tube line on the way back, I would just continue having a surface operator. Like there's no way back to like a line operator anymore.
That's a good question. So from this configuration, it's not clear what's non-invertible about this, right?
Mm-hmm.
Because you can read the equality from left to right or right to left. What's really non-invertible is that if you view it as an operator acting on the Hilbert space, then that operator has occurred. So concretely, you can think about, let's say our space has a non-trivial one cycle. For all we know, that could be the case in our universe. Maybe if you go in that direction, eventually it will come back. So let's assume that's the case.
Okay.
Then you can wrap a two-hoop line around that direction in your space. And that creates some state in your Hilbert space of QED. The claim is that if you act as the operator on this state, it annihilates the state. So the operator, even though it's conserved, it has occurred. So it's non-invertible, and in particular non-invertible. Okay, another trivial application is about naturalness. So Hooft in his 1980s paper introduced his notion of naturalness to say that in a Lagrangian you can impose a global symmetry G, and the Lagrangian should include all G invariant terms with coefficients of order 1 and no fine tuning. One can ask, is the massless QED Lagrangian natural? What forbids us from writing down the electron mass? Actually, there's no ordinary exact global symmetry that forbids you from writing down the electron mass. But now, with the non-invertible global symmetry, we can say that the electron mass term will violate this symmetry. And therefore, the massless QED is natural because of this non-invertible global symmetry. This is to be contrasted with the scalar QED. For the scalar QED, there's absolutely no global symmetry enhancement in the massless form. And that's the reason why there's a Coleman-Weinberg mechanism. Start with the massless point classically, and quantum mechanical effect will generate the mass point. But there's no Coleman-Weinberg for fermion QED. And one way to understand it is that there's an enhanced non-invertible global symmetry for the massless form. But of course, it makes you wonder, how did Hooft think about it back in the 80s? When he introduced the notion of naturalness, he must have thought about QED as an example. Well, let's take a look at his paper. This is a small paragraph from his paper where the section title is called Naturalness in QED. He said that QED is natural, and the relevant symmetry here is the chiral symmetry. But of course, in 1980s, Hooft already knew of the ABJ anomaly. And that's why he added a sentence. He said, we need not be concerned about the ABJ anomaly here because the photon field being abelian cannot acquire non-trivial topological winding numbers. What he said is perfectly correct. But again, it makes you a little bit uneasy about, is there a symmetry or not? And now with this new formalism, you can say that there's an exact non-invertible global symmetry to guarantee the naturalness of it. So we can draw this little timeline. But before 69, everyone thought the axial symmetry is a true symmetry quantum mechanically, but then that leads to the neutral pion decay problem, that leads to the U1 problem. And ABJ came along and said that no, actually quantum mechanically it's not a symmetry. So now we can actually say that it is a non-invertible global symmetry in quantum mechanics. And looking back at history, it's kind of interesting that there's no way that ABJ could have thought about this non-invertible construction, because the fractional quantum host state was only experimentally observed in 1982. That was way before.
So coming back to non-compact case, so what would you say in non-compact case? What is the correct answer?
I would say that there's a symmetry.
There is, but on the other hand, there is also this non-invertible symmetry. It can be written in non-compact case. Also, right?
That's a good question. So it's very easy and cheap to generate non-invertible symmetry. If you hand me your favorite invertible symmetry, I take that operator, I just stack some decoupled TQFT, and I can make a non-invertible symmetry for you. The key point here is that when the gauge group is compact, there is no invertible version, and you have to live with the non-invertible TQFT to cure the ABJ. Okay, and I'll quickly say something about QCD, which works in exactly the same way. In QCD, below the electroweak scale, in the massless quark limit, it has a U1 axial symmetry that rotates the up and down quarks this way. It's an additional factor of sigma. And that U1 symmetry has an ABJ anomaly with the U1 electromagnetic gauge. And by the same construction, we will say that there's a non-invertible global symmetry D in this UBQCD.
By QCD, you clearly mean QCD coupled to dynamical U1, right?
Absolutely. Coupled to dynamical electromagnetic gauge. Now you can ask, how does the IR pion Lagrangian seize or match this non-invertible global symmetry? But the relevant terms for us in the pion Lagrangians are just that for the neutral pion. And here we include the term coupling to the F wedge F with a general coefficient G. For all we know at this point, G could be 0. The non-invertible global symmetry shifts the pion field. And in the next slide, I will show that the equations of motions in the presence of this non-invertible global symmetry will fix the coefficient G for us. That's a very simple calculation. You just insert this defect, say at x equals to 0. There are 3 kinds of field. There's a bulk electromagnetic gauge field, F. There's a pi 0, the neutral pion. And there's a little a auxiliary field living on the operator. And you write down 3 equations of motion for them. And by looking at it for 5 seconds, you see that these 3 equations are only consistent if the coupling constant G is fixed to be this precise value. That's the correct value giving you the dominant neutral pion. So this gives an alternative derivation of the pi 0 FF term from matching the global symmetry, UBQCD, coupled to dynamical electromagnetic. And of course, since the fine structure constant is so small, in the limit when it goes to 0, you can view this, the ordinary argument is using the Takupa matching. And some quick comments on possible generalizations. So our construction does not generalize straightforwardly to the following cases. I should emphasize that it's not to say that these generalizations are impossible, just our tricks don't work straightforwardly. You can ask, what about axial rotation with an irrational angle? That doesn't work because there's no irrational on the whole state. But I encourage you to see these 2 papers for an alternative construction. Also, our construction doesn't work for SUN gauge groups. The short reason is because there's no magnetic symmetry for this. And that highlights the difference between eta prime and pi 0. And finally, our construction does not work for 1 plus 1 DQED the sugar because there's no magnetic symmetry. All right, in the remaining time, I will say something about axiom. So this will be based on an upcoming paper. So I will focus on the axion-Maxwell theory. Theta is a dynamical axion field. It's a compact scalar field. And it couples to the photons with a coupling constant k. And of course, k has to be an integer because I assume the gauge group is 1. When this axion photon coupling is greater than 1, it was noticing this paper. Sorry, I missed a lot of references. There are more references here. There's also a paper by Hikita, Yokoyama, and others. Demonstrating that when k is greater than 1, there's a higher group symmetry. I'm not going to say anything about higher group symmetry, it's just yet another generalized global symmetry. But there doesn't seem to be any interesting generalized higher group symmetry when k is 1. What we will show in this upcoming paper is that there are actually non-invertible symmetries already at the minimal axion photon coupling level. For more general k, there are also non-invertible symmetries, but it's more complicated. But where does that come from? Well, again, one of them is very easy. So people usually say that in axion-Maxwell, you have an anomalous symmetry that shifts the axion. But of course, that's not really an ordinary global symmetry because that shift is broken by the axion photon coupling. Put differently, the Petrin-Quinn symmetry is not really an exact global symmetry, it's anomalous. Now, in this new language, you can say that the shift symmetry is actually a non-invertible global symmetry. Here, I call it a zero-point symmetry with a superscript z is 0, just to say that it's an ordinary symmetry that acts on local fields. So this part of the story works in exactly the same way as in the neutral pion case in the Carroll Lagrange, because the way the neutral pion couples to the photon field is the same as how the axion couples to the photon. What's more interesting is that there's actually a non-invertible one-point symmetry. It's a non-invertible center symmetry. Naively, the axion-Maxwell theory has a center symmetry, shifting the gauge field by a flat connection. But that symmetry is also broken by this term. But what we will argue is that it's resurrected as a non-invertible symmetry. So how do we think about it? In axion-Maxwell theory, the Gauss law is anomalous. The ordinary Gauss law says that d star f vanishes in the absence of charge sources. But in axion-Maxwell, d star f doesn't vanish. It has something on the right-hand side. Let me remind you, divergent E is one of the components of d star f. So because of the anomalous Gauss law, there's no conserved engaging invariant in quantized electric charge in axion-Maxwell theory. And indeed, there's an easy way to see that. So imagine you have an axion string going out of the string. Then you can pair create the monopole and anti-monopole out of the vacuum. You can bring the monopole and anti-monopole around the axion string. By the Witten effect, as they go to the other side of the axion string, they will gain an electric charge, and then the pair annihilates. So it seems that you just generate the electric charge out of nowhere. And that's one way to say that the Gauss law is anomalous.
So when I you former slide, so why do you say the Schur symmetry is not the exact symmetry? Because I just naively think you just get the extra.
But it's not zero.
Also, if you just fill this 3 plus 1, just.
There's a non-trivial instant background integrated.
That's exactly the reason why I put up this slide in the very beginning. We are using number 2. This is symmetry in flat space-time. Yeah. And I completely agree with you. But the whole point of ABJ is that it's not an exact global symmetry. Where was I? Okay, I was here. But in axion-Maxwell, what we can do, we can play the same trick. So we can start with this naive integral of star f corrected by some kind of theta dA term. The integral of this object has a name in the literature. It's a page charge. The page charge is famously not gauge invariant. It's formally conserved. So this U hat operator is also not gauge invariant. But again, we can play the same trick by fixing it with some TQFT on the surface. This time we're in one dimension lower, and we have to use a 1 plus 1 is the gauge. So you can think about this new operator, E1, is supported on any closed to surface, and it's some gauge invariant cousin of the page charge. Let's see how it acts on the electron and the monopole. If you circle this operator D1 around an electron, it just measures the electric charge, or rather more precisely, the exponentiation of the electric charge. However, when it acts on the charge 1 monopole, it just annihilates the vacuum, the monopole. And that shows that it's a non-invertible operator. In this way, you see it's consistent with the anomalous Gauss law we saw in the previous slide. Because in the presence of a monopole, if you try to measure it, then the measurement just collapses. More advancedly, you can consider a charge n monopole, and then a charge n monopoles. Then this operator will act invertibly. So there's a more sophisticated conservation law in axion-Maxwell. If you have a charge n magnetic monopole, then the electric charge is only conserved modulo n because of the Witten effect. When you move a charge n magnetic monopole, you gain n units of electric charge. So your electric charge is always ambiguous modulo n. And this mod n conservation, depending on the magnetic charge, is precisely captured by the non-invertible one-point symmetry, known as a non-invertible Gauss law. And this non-invertible symmetries also lead to universal constraints on the energy scale where these symmetries can be broken.
And this is an example of a non-invertible gauge symmetry.
No, it's a non-invertible one-point symmetry. one-form global symmetry. See?
Okay.
It's not gauge. There's an actual Gauss law operator. It's like in ordinary free Maxwell theory, there's a one-form global symmetry, which is just the electric surface operator.
Okay, fine.
So those are the symmetries of the axion-Maxwell theory. Typically, axion-Maxwell theory arises in the low energy limit of some UV complete model. And the symmetries we discuss here are emergent along the arching flow. So if you start with axion-Maxwell and you go up in energy, some of the symmetries will eventually be broken as you go to the UV. And it's interesting to ask how these symmetries are broken as you go up in energy. And the fact that there are these non-invertible symmetries actually give you constraints on when the symmetries can be broken. In fact, not all symmetries are on the same footing. Some of the symmetries we discussed before, they are kind of subordinate to others, meaning that they cannot exist without the others. They rely on the existence of another symmetry. I'm not going to elaborate too much on that structure, but I'm just going to say that utilizing that kind of hierarchy structure between the symmetries, you can derive universal inequalities. It's symmetry breaking scale. For example, let each shift be the scale where the shift symmetry, more precisely, is a non-invertible symmetry that's broken. Then the inequality tells you that the shift symmetry has to be broken before you hit the dynamical monopole as you go up. And that's consistent with this paper by Gigi Fan, Fraser, Matt Rees, and John Stout from a year ago, where they show that a virtual monopole running in the loops will generate the axion potential flow. So before you find the dynamical monopole, they already run in the loops and give you the axion potential, breaking the shift symmetry. Another inequality you can derive is that as you go up in energy, you will encounter some massive electrically charged particle charged under the gauge group, maybe some electrons. Our generalized global symmetry tells us that that particle has to be smaller than the minimum of the magnetic monopole or the scale of the axion string. That's also consistent with the result from anomaly inflow by Kelly and Harvey, because Kelly and Harvey told us that in axion-Maxwell theory, the axion string will carry ionic degrees of freedom. So before the axion string becomes dynamical, you can imagine a very small axion string that wrap together, and that behaves just like the electrical charge. And this kind of inequality generalized the results of this paper by Brennan and Clay in the case when the axion coupling is greater than 1. All right, so let me just summarize. So in massless QED and QCD, we talked about this non-invertible discrete global symmetry D, labeled by the rational numbers. These are some new global symmetries in QED, and it explains the helicity conservations. It also explains why the massless QED is natural. The trick to construct this new symmetry is to use a fractional from the whole state to cancel the anomaly. And in axion-Maxwell theory, there's a non-invertible one-form symmetry, which gives you a non-invertible Gauss law, explaining the anomalous electric charge conservation. And I think that's it. Thank you.
Do you have any comments on gravitational ABJ?
Oh, that's an interesting question. So I think the non-invertible symmetry D does have a mixed gravitational anomaly, just because the actual symmetry in the free direct fermion does. That means when you turn on the curvature, this operator will no longer be topological. We didn't study that, but I think that's quite interesting. Yeah, I think that's all I can say at this point. It's something on the list. Thanks.
A question. So, so you mentioned that for k bigger than 1, there's high group symmetry.
Right.
So do you see any way, like your non-invertible this 0.1 symmetry is related to the higher group symmetry?
Well, I think, yeah, I think together they form a more complicated thing. And
But the higher group symmetry happens for k bigger than 1.
that's right. So for k greater than 1, the two will mix together into a big category, which I have no idea. I mean, I have some ideas what they look like, but it's hard to work it out completely. It's quite complicated. And you can, yeah.
But would you say that for k bigger than 1, you can derive the same constraints with this hierarchy on symmetry breaking?
That's right.
Just using the non-invertible?
Yeah. Okay. So for k greater than 1, you have more symmetries and you have more inequalities.
Ah, okay.
Yeah. Because you can ask maybe the center symmetry is violated mod k or not.
Sure.
And then you have more scales to talk about.
Okay, any more questions? No, we can thank Shu-Heng.
Is there an example where there's really a complete theory with symmetry is present?
Oh.
What?
Yeah.
Is it just a